Well, here's something more unusual. It's not a rational function this time. It's something going to infinity, but look at the form. This is something of the form infinity minus infinity. Now, infinity minus infinity is one of those things that we call an indeterminate form. You don't know what this is doing, right? Because infinity minus infinity, it depends on how big the infinities are. It could be going to plus infinity. It could be going to minus infinity. It could be going to a number. You don't know. So just as an aside, and we'll see this again and again in this class, indeterminate forms, we've already seen some. The big one that we've seen a lot of is 0 over 0. We already saw that it could be 0, it could be infinity, it could be a number. Usually when we've been using it, it's been a number because that's more interesting. Infinity over infinity is like that as well. Like the very first example that I did with limits going to infinity, right? If we put in infinity, you get infinity over infinity. What's that? That doesn't tell me anything. It ended up being 4/3 or something, right? All three of the examples actually that we had of rational functions, if you just stick in infinity, you get infinity over infinity. And we saw that either it went all different places. So these are the most common indeterminate forms, but you also have infinity minus infinity and 0 times infinity. So those are all four that we'll see fairly often. There's some weird ones like infinity to 0 and stuff like that that we won't really be working with much in this class. But these are the four main ones that that just sort of pop up naturally. When you see those, all of them, it means I need to do more work. That's what it means, because you don't know what it's doing. This one particularly is a bit of a mess because it has that square root. Unlike one of the previous examples where we had to worry about the sign of the square root, we don't have to worry about that here because we're taking the limit as x goes to positive infinity, so that issue doesn't pop up in this particular example. But you can see that it's a weird infinity minus infinity, and we're going to have to do something with it to make it make sense. Usually if you have one of those, you try to factor it or something, but this has a square root. You can't factor this the way it is. So as always, right, we're going to try and multiply it by the conjugate radical and hope that that makes sense and that works out, because these kind of things, that's our best hope. Now, I'm multiplying the top. Of course, I also have to multiply the bottom with the same thing, because what I'm doing is I'm multiplying by 1. I can't change the thing. I'm multiplying by 1. Okay, so now it looks like maybe I just made myself a horrible mess. Let's just see what happens. Well, at least I can say the bottom is no longer infinity minus infinity. It's infinity plus infinity, right? So at least it's going to infinity. That's all I can say about that, right? The minus is what is the problem here, because you don't know, something might be being taken away. If I'm adding two things that are going to infinity, they're definitely going to go to infinity. They're just going to go faster, right? Because they're adding to each other. All right, now what's the top? The top is going to be a squared minus b squared. So the a squared is that, and then the b squared is that. Okay, so these cancel out. And now I have 3x in the top and this garbage in the bottom. You know what? I'm just going to erase this bit about indeterminate forms. Okay. in the previous videos. We've got a rational function that's going to infinity. We're going to do the same step. We're going to multiply top and bottom by 1 over x. I say 1 over x because it's the highest power. So here's an x, here's a square root of x squared, so that's also an x. So 1 over x, both top and bottom, is my next step. Okay, the top is clearly 3. The bottom, I've got a little bit of work to do there. So, I can write this as this, 4x squared plus 3x all over x squared, because I'm taking the x underneath the square root, so I get that. And then this is just going to be 2x over x. So, when I clean that up a little bit, I'm going to get 4 plus 3 over x, and then plus 2. Okay, so as x goes to infinity, the only x that's left is this 3 over x, square root of 3 over x. And I know it's square root, but I can take a thing under the square root. This guy is still going to go to 0 as it goes to infinity. So what I'm left over with is 3 over root 4 plus 2, so that gives me 3/4. So this mass, actually, the first one, right, well, that's still the same thing, but we see that function, it is infinity minus infinity, but it does have a nice horizontal asymptote of 3/4. Let me give you a brief example of another infinity minus infinity, which we can quickly show is not so well behaved. I can look at something sort of simple like this. You already know this basically is a parabola, so you know as x goes to infinity, it's going to be infinity, right? But it's got an infinity to minus infinity form, so you kind of have to do something with it. One thing you can do with it is immediately you can factor out an x. Okay? And now I'm looking at two things, infinity, and it's infinity times infinity, which is clearly also going to go to infinity. That wasn't one of our indeterminate forms, because of course if both things are going to infinity and we're multiplying them, it's going to go even faster, right? So in a simple case like this, you could do something like that. In a more complicated case like we had in the previous problem, it's more interesting. You have to do a lot more to get it into sort of a form where you can see what's really going on. And paradoxically, with the first example, it seemed like I made things a lot worse because I multiplied top and bottom. I multiplied this big fraction. I had something that at least it was just like one line, and then I end up with this rational function and all this garbage. But it turned out that that was what I needed in order to be able to take the limit and see what was going on. So, though most of the time we're wanting to simplify as much as possible, sometimes we have to make it worse before it gets better, right?